In mathematics, we usually write an expression like a plus b. The operator plus sits between its two operands. This is called infix notation because the operator is placed in the middle. Human-friendly, most textbooks and calculators use it. Requires rules, precedence, associativity to know which operator to apply first. Needs parentheses to override the default order. Postfix, also called reverse Polish notation, RPN, moves the operator after its operands, a b+. The computer reads left to right, pushes operands on a stack, and when it sees an operator, it pops the needed number of values, applies the operator, and pushes the result back. No parentheses are needed. The order is encoded by position. Very easy to evaluate with a stack, which is why many calculators, HP, some programming language interpreters use it. Prefix, also called Polish notation, puts the operator before its operands. Plus a b like postfix, prefix also eliminates the need for parentheses, but the scan direction is usually right to left, or you can use a stack with a left to right scan by pushing operators first. Unambiguous without parentheses. Often used in compilers' internal representations, because the tree structure of an expression can be built directly from the prefix string. When we write an infix expression, the computer must decide which operation to perform first. This decision is made using two concepts, precedence and associativity. Precedence is a ranking of operators. Multiplication, division, and modulus usually have higher precedence than addition and subtraction. For example, in 3 plus 4 times 5, the multiplication is done before the addition, yielding 3 plus 4 times 5 equals 23. Associativity tells how to group operators of the same precedence. Most binary operators are left associative, meaning they are evaluated from left to right. For example, 10 minus 5 minus 2 is interpreted as 10 minus 5, then minus 2, which equals 3. Exponentiation is often right associative. 2 to the power 3 to the power 2 means 2 raised to the power of 3 raised to the power of 2, which equals 512. These rules are like traffic lights at a busy intersection. Precedence is the road hierarchy, and associativity is the direction of traffic flow when two cars reach the same lane at the same time. The most common way to turn an infix expression into postfix is the shunting yard algorithm invented by Dijkstra. It uses a stack to temporarily hold operators and parentheses. Here is a step-by-step description with a simple example: a plus b times c to the power of d minus e to the power of f plus g times h minus I. Step 1. Create an empty output list and an empty operator stack. Step 2. Scan the infix string from left to right. If the token is an operand, for example A, append it to the output. If the token is an operator, while the operator at the top of the stack has higher or equal precedence and the same associativity, pop it to the output, then push the current operator. If the token is an opening parenthesis, push it onto the stack. If the token is a closing parenthesis, pop operators to the output until an opening parenthesis is encountered, and discard both parentheses. Step 3. After the scan, pop any remaining operators onto the output. Applying the steps yields the postfix form: a bcd to the power of e minus fgh times plus to the power of times plus I minus. Why a stack works? Think of the stack as a line of people waiting to cross a bridge. The most recent person at the top of the stack crosses first, which matches the rule that the last operator seen inside the most inner parentheses must be applied before the earlier ones. Converting infix to prefix is similar to infix to postfix but with a few twists. A common method is to reverse the infix expression, swap each left parenthesis with right parenthesis and vice versa, apply the infix to postfix algorithm, and finally reverse the resulting postfix string. Steps with example: double left parenthesis, a minus b close parenthesis, divided by double left parenthesis c plus d close parenthesis times e close parenthesis. Step 1. Reverse the string becomes right parenthesis, e star right parenthesis d plus c left parenthesis slash, b minus a left parenthesis. Step 2. Swap parentheses becomes left parenthesis e star left parenthesis d plus c right parenthesis slash left parenthesis, b minus a right parenthesis. Step 3. Run the shunting yard algorithm as described above to get postfix of the reversed expression. EAB minus CD plus times divided by. Step 4. Reverse the postfix result becomes slash star plus DC minus BA E, clean slash star plus DC minus BA E. The resulting prefix expression is slash star plus DC minus BA E. Analogy: imagine reading a recipe backwards. You first note the final dish, then work out which sub-steps must have happened just before it, and so on. Reversing the expression mimics this back to front reasoning, allowing us to reuse the familiar postfix conversion logic. Explanation: evaluating a postfix expression is straightforward with a stack, because the order of operations is already encoded. Algorithm using the postfix 623 plus times 5 minus, which corresponds to 6 times 2 plus 3 minus 5. Step 1. Scan tokens from left to right. Step 2. If the token is an operand, push its numeric value onto the stack. Step 3. If the token is an operator, pop the required number of operands. For binary operators, pop 2. First popped is right operand, second popped is left operand, apply the operator and push the result back. Step 4. After the last token, the stack contains exactly one value, the answer. Execution of the example: push 6 onto the stack, push 2 onto the stack, push 3 onto the stack. Encounter plus, pop 3 and 2, compute 2 plus 3 equals 5, push 5 onto the stack. Encounter times, pop 5 and 6, compute 6 times 5 equals 30, push 30 onto the stack. Push 5 onto the stack. Encounter minus, pop 5 and 30, compute 30 minus 5 equals 25, push 25 onto the stack. Result equals 25. Real-world analogy: think of a conveyor belt where each item is a number. When a worker, representing an operator, arrives, they take the 2 items at the end of the belt, combine them as instructed, and place the new item back on the belt. The process repeats until only one item remains. Prefix evaluation is the mirror image of postfix evaluation. Because operators appear before their operands, we usually scan the expression right to left, or we can reverse the string and use the same left to right logic. The stack algorithm is: Step 1. Scan the prefix string from the rightmost token to the leftmost. Step 2. If the token is an operand, push it onto the stack. Step 3. If the token is an operator, pop the required number of operands. First pop is the left operand, second pop is the right operand because we are scanning backwards. Apply the operator and push the result. Step 4. After processing all tokens, the stack holds the final value. Example prefix: minus times 6 plus 235, the same expression as before. Execution: scan 5, push. Scan 3, push. Scan 2, push. Scan plus pop 2 as left operand and 3 as right operand. Compute 2 plus 3 equals 5, push. Scan 6, push. Scan multiply pop 6 as left operand and 5 as right operand. Compute 6 times 5 equals 30, push. Scan minus pop 30 as left operand and 5 as right operand. Compute 30 minus 5 equals 25, push. Result equals 25. Analogy: imagine reading a sentence backwards to understand its meaning. Each time you encounter a verb, which is an operator, you look at the 2 words that follow it, which you have already seen while reading backwards, and combine them into a new phrase, continuing until the whole sentence collapses into a single idea. Explanation: exam questions on expression conversion and evaluation often follow a predictable pattern. Here are 3 typical types, each with a short example and what the examiner expects. 1. Infix to postfix conversion. Question: convert the infix expression a minus b times c plus d divided by e to postfix. Solution steps: scan left to right, use a stack for operators. Resulting postfix: a bc times minus de divided by plus. What to show: the intermediate stack states or a clear table of actions: operand arrow output, operator arrow push or pop. 2. Infix to prefix conversion. Question: write the prefix form of x plus y times z minus w. Solution steps: reverse yields w minus z times y plus x, swapping parentheses. Convert to postfix yields w z y x plus times minus. Reverse result yields minus times z plus y x w. What to show: each transformation step. Many graders give credit for the method even if the final string has minor spacing differences. 3. Evaluation of postfix or prefix. Question: evaluate the postfix expression 413.5 divided by plus, assuming integer division. Solution: push 413.5. Slash yields 13 divided by 5 equals 2 integer. Stack 4 2. Plus yields 4 plus 2 equals 6. Result equals 6. What to show: a step-by-step stack trace. These problems test 3 skills: understanding of precedence, ability to manipulate a stack, and careful arithmetic. Practice by writing down the stack after every token. That habit earns full marks. Parentheses or other grouping symbols like curly braces and square brackets are the traffic controllers that force a specific evaluation order overriding normal precedence. Both conversion algorithms must treat them specially. During infix to postfix using the shunting yard method. When an open parenthesis is read, push it onto the operator stack without outputting it. It acts as a sentinel. When a close parenthesis is encountered, repeatedly pop operators from the stack to the output until the matching open parenthesis is on top. Then pop and discard the open parenthesis. This ensures that all operators inside the parentheses appear before any operator outside, exactly as the parentheses dictate. During infix to prefix using the reverse method. After reversing the expression, each original open parenthesis becomes a close parenthesis and vice versa. The algorithm then handles them exactly as in the postfix case. The swap is essential because after reversal, the opening side of a group appears on the right side of the reversed string, and we need to treat it as a closing delimiter for the stack logic to work. Real-world analogy: imagine a group of children playing a game where a leader operator can only give instructions to children inside a fenced area called parentheses. When the fence is entered, the leader must wait, pushing onto the stack, until the children inside finish their mini-game, then the leader can act. The fence ensures no instruction leaks outside the designated area.